10 million aluminum cans are discarded across the globe every single hour. This volume of metal waste is so massive that it could theoretically bury an entire metropolis the size of Los Angeles under a layer of metallic refuse. Why is the collection of these seemingly worthless containers considered one of the most efficient industrial loops in existence? One might assume that the material degrades after being melted down and reformed several times. But in reality, aluminum possesses a unique atomic structure that allows it to be recycled endlessly without any loss in its physical quality or structural integrity. The rebirth journey begins inside highly automated recycling plants. Industrial systems automatically sort the incoming scrap before high-speed blades shred the metal into small, uniform fragments. One can notice how mechanical separators and air currents systematically remove paints, coatings, and other impurities from the shredded material. The process is only gaining momentum. After cleaning, the aluminum enters furnaces where it is heated to over 660 degrees Celsius until it transitions into a liquid state. The equipment gradually refines the melt step by step until the secondary metal is indistinguishable from primary aluminum. 70 million tons of aluminum are manufactured globally every single year. This immense figure highlights the metal's critical role in the construction of window frames, automotive components, and even high-performance aircraft fuselages. But this enormous scale of production simultaneously creates a logistical and environmental challenge as the volume of discarded scrap rises. Transition to the next level. Recycling has become the primary solution to this growing surplus. 35% of the total aluminum used worldwide each year is now sourced from recycled materials rather than raw mining. This shift is driven by the fact that recycling aluminum consumes only 5% of the energy required to extract the same amount of metal from bauxite ore. The result is a drastic reduction in operational costs and a significant decrease in carbon dioxide emissions. It is visible how this efficiency has preserved the world's metal supply over decades. 75% of all aluminum ever produced in human history remains in active use today, circulating through a continuous cycle of melting and fabrication. The molten metal eventually flows into molds to take on new forms, ensuring the material remains within the industrial economy. Tens of millions of tons of aluminum are collected every single year from a vast network of sources, establishing the United States as a global leader in the recycling sector. Why does the collection process function on such an immense scale across municipal waste facilities and industrial networks? It would seem that simple scrap gathering is a minor logistical task, but the inherent economic value of the metal dictates the intensity of the system, as a single discarded beverage can is worth several times more than a plastic bottle, providing a constant financial incentive for both individuals and corporations. At first glance, the initial gathering of waste appears straightforward, but in reality, this stage dictates the total effectiveness of every subsequent industrial operation. Tens of thousands of trucks packed with used containers and factory offcuts roll steadily into massive staging yards across the country. One can notice how each vehicle stops on a heavy-duty scale to be weighed and recorded before the cargo is released. The metal begins its return to the modern world here, at the threshold of rebirth, where it is prepared to take on an entirely new form. But this is just the beginning. The yard operates at a relentless pace. The process is only gaining momentum. Immense heaps of metal rise like silver hills across the site, as beverage cans and industrial scraps merge into a single stream. It is visible how technicians perform rapid initial checks on the ground, immediately identifying and rejecting shipments tainted by dangerous substances or excessive contaminants. Every single day, thousands of tons of material pass through this gateway, where the sheer volume of metal requires constant monitoring and hydraulic movement. Heavy containers tip slowly with the hiss of hydraulics, releasing their contents onto wide conveyor systems. Everything only gets more complicated. Long lines of extended conveyor belts move the aluminum scrap forward in a continuous, unyielding stream. Why is the material scanned thousands of times every second by optical sensors? High-speed processing is the only way to manage the incoming flow. These digital eyes recognize the specific reflective properties and unique coloration of the metal with absolute precision. Right after the scan, powerful magnets extract ferrous impurities, while precisely timed bursts of compressed air propel the aluminum away from paper, plastic, and other lightweight debris. One can notice the separation system working layer by layer to transform a chaotic blend of waste into a uniform material. Transition to the next level. The equipment gradually organizes the metal into shimmering silver piles that are now chemically consistent and carefully regulated. It only looks obvious to sort materials by hand, but in reality, only automated sensors and air-jet systems can handle the speed of this industrial transformation. From this point forward, the aluminum flow is prepared to move deeper into the recycling chain for further processing. The material leaves the sorting stage, transitioning into a calm stage where its chemical purity is guaranteed. Thus ends the critical phase of collection and primary separation. 660 to 750 degrees Celsius is the temperature range where aluminum scrap undergoes its final metamorphosis within the furnace. Why must the heat be maintained with such rigid precision? At first glance, melting metal seems like a straightforward thermal reaction, but in reality, the slightest deviation can cause the loss of critical alloying elements or allow the aluminum to oxidize into useless slag. The molten liquid remains inside these sealed systems where temperature, airflow, and the rate of material mixing are regulated simultaneously to ensure a perfect melt. Hundreds of kilograms of scrap move toward the enormous shredding unit to begin the reduction phase. Conveyor belts carry a mixture of beer cans, food containers, and thick industrial offcuts into the reach of counter-rotating steel rollers. One can notice how the metal breaks apart instantly under the extreme crushing force of hardened teeth, sending sharp metallic impacts ringing across the factory floor. It gets more complex further on as heavy crushing hammers and spinning blades work in tandem with the rollers to fracture even the most rigid components. The system runs with remarkable accuracy, as if every movement were pre-programmed by the facility's control center. Beneath the harsh glow of industrial lights, silver fragments flow in a non-stop stream, spilling onto lower conveyors like a glittering cascade. A vibrating screening system regulates the output size, ensuring every piece of shredded aluminum reaches a uniform dimension. But this is just the beginning. The shredded aluminum fragments are fed directly into large-scale industrial furnaces, which serve as the core of the entire recycling operation. Depending on the scrap type and the intended final application, the facility utilizes reverberatory furnaces, rotary kilns, or electric arc furnaces. The equipment gradually draws the material in through a top hatch or a tilting chute as the metal begins its transition into a liquid state. Mechanical agitators or controlled air injection systems keep the aluminum in constant motion to prevent cold spots within the melt. Some furnaces incorporate heat recovery technology to maximize energy efficiency, while multi-stage filtration systems capture aluminum oxide dust. Throughout the entire smelting process, thermal sensors and chemical analyzers run without interruption to verify that every batch meets strict technical standards. The process is only gaining momentum. This stage represents the climax of the recycling chain where pressure, heat, and mechanical control converge into a single action. Even once the aluminum has completely melted, it still holds countless hidden contaminants that are invisible to the naked eye. Paint coatings, furnace dust, and traces of industrial oils remain suspended within the silver liquid. To remove these unwanted elements, the facility initiates a refining stage directly inside the furnace chamber. One can notice how a specially formulated flux is added to the melt to begin the purification. As the reaction occurs, the flux binds with impurities to create a lightweight dross layer that floats to the surface like a thick crust. This layer is then skimmed away, either mechanically or by hand, to leave behind a purified metal. Everything only gets more complicated as advanced setups inject inert gases such as argon or chlorine at low pressure. Tiny bubbles pass through the molten aluminum, capturing excess oxygen and hydrogen and lifting them to the surface for removal. Temperature control continues throughout this degassing phase to ensure the purity levels meet the requirements for the casting stages ahead. The outcome is a continuous flow of clean, molten aluminum ready for the next stage of transformation. The molten stream goes further along the production chain. 100% of the molten aluminum moves toward the casting area once it achieves the required level of chemical purity. It is at this precise moment that the liquid metal begins to acquire its first clearly defined physical shape. Why is this transition from a formless mass into structured units considered so critical? The process marks a fundamental shift from a fluid state into solid blocks that can be measured, handled, and transported across the industrial facility. This transformation ensures the raw material is ready for the next stage of manufacturing. The casting station relies on molds crafted from steel, graphite, or specialized heat-resistant materials. Pouring begins as the aluminum flows into molds that vary in orientation based on the final product requirements. These include vertical molds for heavy ingots, horizontal molds for thick slabs, or continuous casting systems that utilize water-cooled forced solidification. One can notice how the equipment gradually regulates the pouring speed, the mold temperature, and the cooling intensity with absolute precision. But this is just the beginning. The process is only gaining momentum as the molten stream fills the voids. At first glance, the flow of metal seems simple, but in reality, every variable must remain in a state of perfect balance. If the liquid aluminum flows at a speed that is too high, gas pockets or surface cracks can form within the structure. If the mold is too cold, the solidification occurs unevenly, which inevitably creates internal defects. Therefore, the operators must guide the steady stream through the narrow channels without the slightest deviation. Any small change in the flow rate can distort the entire shape of the finished piece. Modern plants utilize fully automated casting systems to maintain this delicate equilibrium. In some semi-manual operations, experienced workers still regulate the flow themselves with manual controls. This specific task demands split-second precision to prevent waste or structural failure. Everything only gets more complicated as the metal cools. Once the aluminum has solidified within the mold, a hydraulic mechanism applies gentle upward pressure to the base. It is visible how the metal rises with the hiss of hydraulics, freeing the solid unit from the steel walls. Mechanical clamps secure the heavy ingot, which often reaches a weight of several dozen kilograms. The manipulator lifts the block out of the casting channel and sets it onto a parallel steel conveyor with a slow, controlled rotation of the boom. The sound of metal sliding and scraping reverberates through the foundry as the surfaces make contact. It gets more complex further on. Each ingot's surface still emits a faint red glow from the residual heat trapped within the core. One after another, the ingots are released in perfect synchronization with the movement of the machinery. The blocks are arranged neatly along the moving belt, forming a continuous line of silver-colored metal. Sensors immediately scan each individual piece, verifying the shape and dimensions to confirm that no distortion occurred during the release phase. The camera glides along the conveyor as rows of solid aluminum ingots continue their steady advance. They are aligned like uniform metal blocks, signaling that the production cycle has reached its successful conclusion. The material leaves the casting zone, transitioning into a calm stage. 8 to 10 inches. This is the substantial initial thickness of an aluminum ingot as it emerges from its mold. Why must these massive blocks undergo a grueling thermal treatment before they can be shaped? At first glance, the metal appears solid and unyielding, but without preheating, the internal structure would fracture under the force of the machinery. The furnace gradually raises the temperature of the blocks to reach a state of precise softening, ensuring the material is perfectly prepared for the mechanical stress of the rolling stands. The aluminum moves steadily into the jaws of counter-rotating steel rollers. Immense pressure is applied as the rollers grip the metal, simultaneously compressing the thickness and stretching the length of the block. One can notice how the equipment gradually exerts hundreds of tons of force to displace the molecular layers of the aluminum. This operation is not a single event, but is repeated across a long sequence of multiple rolling stands. But this is just the beginning. Everything only gets more complicated as the gap between each pair of rollers narrows with calculated precision. The ingot, which started as a heavy slab of 8 to 10 inches, is reduced into a thin and uniform metal sheet through constant mechanical transformation. It is visible how the metal elongates under the speed of the rotation, turning from a block into a moving ribbon. A fine water mist cooling system operates continuously to stabilize the surface of the aluminum. This prevents the formation of cracks or structural deformations that would otherwise be caused by the accumulation of excess heat during the compression. The process is only gaining momentum. By the final stage of the hot rolling cycle, the metal reaches its specified thickness, which can be as thin as just a few hundredths of an inch. The continuous strip is then guided forward by automated conveyors and wound tightly into large silver-colored coils. It only looks obvious to store the metal in this way, But in reality, coiling is the most efficient method for transporting thousands of feet of material. These standardized semi-finished coils are now ready to be transferred to the next stages of production, including cold rolling, precision cutting, or industrial stamping. The material leaves the rolling line, transitioning into a calm stage of preparation for its final application. Hundreds of millions of aluminum cans circulate through the global economy every single day, becoming an invisible but essential infrastructure of modern refreshment. Why is this specific container so ubiquitous in every supermarket, cafe, and household? One might assume its purpose ends the moment the tab is pulled and the contents are consumed. But in reality, the conclusion of a drink is merely the beginning of a complex logistical and metallurgical crossroads that determines whether the material remains a resource or becomes a permanent liability. The transition from a consumer product to a raw material occurs at the recycling bin. One can notice how the empty containers are sorted into distinct streams, where their potential for near-endless renewal is finally unlocked. It seems simple to just dispose of a container, but this single choice dictates the entire life cycle of the metal. In regions where deposit return systems are active, more than 80% of all cans are successfully reclaimed. The process is only gaining momentum. Within a span of just a few weeks, these collected items are processed and transformed back into identical new products. But this efficiency is not a universal standard. Aluminum is one of the most sustainable materials ever engineered by industrial science, yet its longevity depends entirely on human intervention. Cans that are discarded into general household trash undergo a very different fate, effectively becoming an environmental burden as they are diverted away from the production loop. The camera glides along the massive piles of unsorted waste where valuable metal is lost to landfills. It only looks obvious that a material this valuable would always be saved, but in reality, the lack of proper sorting breaks the technical cycle. Every instance of a consumer placing a container into a designated recycling bin serves as a physical trigger for the green cycle to continue. It is a calculated act of resource management that prevents the metal from being abandoned. One can notice the steady flow of reclaimed aluminum as it moves toward the melting furnaces for purification. This choice ensures that the material maintains its endless journey through the industrial chain rather than stagnating in the earth. Thus, the metal reaches a state of readiness for its next transformation, allowing the cycle to repeat without the need for extracting new raw ore. 100% of aluminum has the potential for infinite rebirth, creating a closed-loop cycle that functions without a terminal point. Why is this metal capable of such a transformation when others degrade? The atomic structure of the aluminum remains entirely unchanged during the melting process, allowing what once appeared to be discarded scrap to undergo purification and return to a high-purity state. One can notice how the molten metal flows from the furnace into molds with a mercury-like luster, transitioning from waste into a structural resource. But this is just the beginning. The material returns to the industrial cycle in a vast array of functional forms. From the thin walls of beverage cans to the rigid profiles of window frames and even the high-tolerance alloy components required for aircraft fuselages, the metal retains its mechanical properties through every iteration. It only looks obvious that the process is purely industrial, but in reality, the chemical stability of the aluminum ensures that the secondary metal is identical to the primary material extracted from ore. The camera glides along the automated sorting lines, where sensors identify and separate the various alloys with millisecond precision. This circular movement of resources is a measurable technological achievement that relies on the physical properties of the element itself. The process is only gaining momentum as global systems integrate more secondary material into the production chain. Everything depends on the singular action of placing the material into the designated recycling stream rather than a landfill. This decision determines whether the journey of a specific object concludes prematurely or continues through an endless sequence of melting and reshaping. The equipment gradually processes millions of tons of such discarded items, ensuring they contribute to a sustainable industrial future. The true value of this recycling chain becomes visible through the massive energy savings achieved compared to primary smelting. One can notice the difference in energy consumption, which drops by 95% when using scrap instead of bauxite. The material leaves the furnace in a shimmering stream, moving further along the production chain to become something new, Thus ends one of the key stages of aluminum's transformation, as the metal is ready to move to the next processing phase without haste.